was a small child, I used to sit with my grandmother and look at the night sky. She'd tell me things about the universe, and we'd try and count the stars. Turns out pretty much everything she told me about the universe was wrong, but that love of the night sky that she instilled in me persisted and translated into a career in astrophysics. Now I use the world's largest telescopes to study the heavens. Unlike when I was a child, though, it's not the optical part of the spectrum that I'm using. I'm a radio astronomer, and I use arrays of radio telescopes to literally map the universe in a different light. These are some of the instruments that I've used in my career. They're located all over the world. Now, some people believe that radio telescopes can't produce beautiful images of the heavens. I think those people are wrong. Here you see an image taken with a telescope in Western Australia called the Murchison Widefield Array, or MWA for short, which is of our galaxy, the Milky Way, shown in 3 radio colours. You see beautiful glowing blue regions of hydrogen gas and circular yellow features, which are supernova remnants, the remains of the most spectacular way a star can die. There is much science to be extracted from this image, and all of it is fascinating in its own right. But today, I'm here to talk to you about the process of extracting that knowledge and how it has to change. Traditionally, astronomers have used a technique called eyeballing to find interesting objects in the universe, and that is literally looking at images from telescopes and writing down where interesting sources are. Here you see a group of women computers at Harvard in around 1900. That is literally what they were called, women computers. And what they're doing is they're holding magnifying glasses and they're looking at optical plates from a telescope and writing down the positions of interesting sources. My first job in astrophysics nearly 20 years ago was almost exactly the same. I was hired to look with a magnifying glass at optical plates and write down the positions of planetary nebula. Now, computing has come a long way in 20 years, so the question is, do we still do science this way? Yes and no. These are my research assistants last year, looking at an image of 3/4 of the sky, taken again with the Murchison Widefield Array telescope, cataloguing it and looking for interesting objects. This is the image that they were looking at. So this is also in 3 radio colours, and there are hundreds of thousands of extragalactic objects in this image. So every single one of those dots that you can see there most likely denotes a galaxy with a supermassive black hole at its core. That is a black hole with a million times the mass of our sun. Every single dot in that image. Now, it would be impossible to count those by hand, and we didn't. We used a computer, and we applied what's called a thresholding algorithm. At their core, thresholding algorithms are very simple. What they do is they look for groups of pixels which are together and above some brightness threshold. So if we take part of that image here, now in 1 color, and we look at the brightness distribution through that image, we can then ask a computer to apply a threshold, which is that red line, to say which pixels are above and below the line. And that's really easy for it to do. But it is absolutely hopeless at finding things which are faint or diffuse or fuzzy. For example, take this radio galaxy. So what you can see here is a core in the center, a dark spot, which is where your supermassive black hole is, and then 2 very fuzzy, faint, diffuse blobs sticking out either side. So those are the results of the black hole throwing out electrons at close to the speed of light. Now, to give you some sense of scale, this thing is 3 million light years across. So even traveling at the speed of light, which is 300,000 kilometers per second, it would still take you 3 million years to get from one side of that object to the other. Every single one of those dots that I showed you in the image of 3/4 of the sky would look like this if we imaged it at high enough resolution. So that's what we're dealing with. So your eyes can easily see those fuzzy blobs, and you can see that there's a core, and I've told you what a radio galaxy is, so you can put that all together and say, okay, aha, I see it. Let's see what a thresholding algorithm does. It only finds what's in those red boxes. So it totally misses all of the faint, fuzzy, diffuse stuff. So we are still reliant on humans to find these things. We are still doing science the same way as the women computers at the turn of the last century. The trouble is, astronomers are driven to map more and more of the heavens in greater and greater detail, and that drives us to build larger and larger radio telescopes. This gives us a big data problem. Right now, we are in the process of finalising the design for one of the world's largest radio telescopes, the Square Kilometre Array. The SKA is going to be built in South Africa and Australia. It's a project which involves 11 countries, 500 scientists and engineers, and will produce 130,000 radio antennas. It's on scale of the Large Hadron Collider in terms of complexity of design. Now, there's lots of science that you can do with this telescope, but I'm going to sum it up in one soundbite, which is to say that we are building a machine which is going to make the highest resolution, fastest frame rate movie of the evolving universe ever. Now, those of you that have dealt with video know that it uses a lot of data, and the SKA is no different. When we switch it on, it's going to collect 160 terabytes of data per second. That's 35,000 DVDs per second. So this is most certainly a big data project. Now, that's the raw data rate. When we mix it down to create frames or images in our radio movie, we're still accruing 1 petabyte of data per day. When people think about big data projects, they think they have something like this. They think that you've got an interconnected series of well-curated information from which you can extract knowledge. Typically, what we actually have is this, an unstructured mess. So this is a problem. Now, the problem with the SKA is, like the MWA, we still have to sift through all these data to find interesting sources. But the SKA is going to produce 360,000 times more data than the MWA, which would mean I would need 360,000 people to spend a year to find all of those objects. So there has to be a better way. The problem that we have is that we're going to turn this thing on, and we think we're going to understand something new about the universe, but really, we're going to be like this dog drowning in data. So, astronomers are not the only people with this problem. As we go through an exponential technology explosion, the big data challenge will affect all of our lives. So everything from syncing your health records, to understanding banking transactions, to having self-driving cars, all of these things are impacted by big data. If we want to live in a data-connected future, we have to transform that data into knowledge. And the only way we can do that is coming up with new techniques, not just to collect data, but to curate it, analyze it, and store it. So astronomers are doing this to understand the universe. We're looking at the big data challenge to understand the universe. But we can't do this alone. We need to come together as a community to help create these new knowledge extraction techniques to be able to live in the future we want. If we want smart cities, if we want to better understand climate change, and if you want to do what I want to do, which is better understand the universe, this is a challenge that we need to work together on. So, when I was a small child, my dream was to count the stars. Today, my dream is to build the machines that will count them for me. Thank you.
Thank you, Melanie.